Okay, imagine this. You walk into a building, and it almost feels, well, alive. Like the walls subtly shift to let in just the right amount of sunlight. The temperature adjusts itself perfectly through the day.
Sounds a bit like sci-fi, doesn't it?
It really does. But what if the actual materials used to build things could sense their surroundings and react? For anyone listening who wants to grasp these big shifts shaping our future, but, without drowning in technical jargon, that's exactly what we're tackling today. We're doing
hmm
a deep dive into the world of smart materials.
Exactly. We're moving beyond just static bricks and mortar and looking at materials that have, well, a kind of inherent intelligence.
So they're not just passive.
Not at all.
It-
They can actively react and adapt.
Mm.
And this is transforming architecture, interior design, even everyday products we use. Think of this as your concise guide to how these responsive materials are really starting to change our physical world.
And guiding us through this is a fantastic resource, the book Smart Materials in Architecture, Interior Architecture and Design. It's a pretty detailed look at this whole field.
It really is comprehensive.
So our mission here is to pull out the most crucial bits, the really fascinating stuff, basically give you those aha moments. So you get a clear picture of what's happening now and maybe what's coming next.
Get you up to speed quickly.
Exactly. Okay, so let's start at the beginning. What actually makes a material smart? What's the fundamental idea?
Right. At its core, a smart material has this uh, remarkable ability to change one or more of its properties when it encounters some kind of external stimulus.
Okay, stimulus like what?
Well, it could be quite a range. Things like light, temperature changes, physical force being applied, electric fields, even changes in the chemical environment around it.
So it's not just inert stuff, it has this sort of built-in trigger and response.
That's a good way to put it, a trigger and response system.
And how does that response actually happen? Is it always the same mechanism?
Well, no, there are primarily two ways this change can happen. Sometimes it's a direct physical reaction. Think about like pressing a spring, it just deforms directly, no energy conversion needed, really.
Mm-hmm.
Other times it's a bit more complex. The material might go through an energy conversion process. For instance, a change in temperature could trigger an internal chemical reaction, and that reaction leads to the change in its shape or color or whatever.
Ah, interesting. So direct reaction or via energy conversion. Okay, so what kinds of properties can actually change? Give us a feel for the range here.
Well, the range is surprisingly wide, actually.
Mm,
A smart material might, say, change its physical size or its overall shape.
right.
It could change its color or just how it looks visually, even its acoustic properties, how it absorbs or transmits sound, or maybe the scent it gives off.
Wow, even scent.
Even scent. And we also see changes in the adhesion, how sticky it is, or the emission of light. Some can even generate electricity.
Generate electricity from the material itself.
Yes, or store energy,
Mm.
or even capture and release gases or water.
Okay, that's an incredible list of possibilities. It makes you think, though, with all that potential, why aren't these things everywhere already? The source talks about how building technology has evolved. It says it's not just about spectacular designs anymore, is it?
Exactly. The book makes a really strong point that the biggest changes in architecture over, say, the last 25 years haven't just been about the flashy, iconic buildings. It's more about the quieter, but maybe more profound advances in building technology and automation.
Hmm.
It's the innovative materials, the products, the construction techniques. That's what's truly shaping how we build now.
So what's pushing this move towards smart materials in buildings specifically? What are the main drivers?
There are a few key things pushing it. One is simply a desire to give buildings more functions, to make them do more than just provide shelter.
Right, more capabilities.
Yeah. And architects and designers are always looking for new ways to express ideas, both functionally and aesthetically. Plus, and this is critical, there are growing ecological and economic pressures. We need more efficient, more sustainable ways to build and operate buildings.
And this leads to what the book calls the next generation of buildings. What does that look like?
Well, the vision is for buildings that are highly ecological, yes, but also technologically advanced. Structures that have a degree of, inherent intelligence.
Intelligence, meaning they can react.
Exactly. They can actively react and adapt to their immediate surroundings. Not just obvious things like sunlight and temperature, but maybe more subtle factors too. They're
Yeah.
designed to be, well, dynamic.
Sounds very efficient, comfortable too, maybe?
Yeah.
But there's that cautionary note in the text, isn't there? The example of the Institut du Monde Arabe in Paris.
Ah, yes. That's a really important point about the human side of things.
What happened there?
Well, it had these incredibly sophisticated mechanical photo shutters, like camera apertures, designed to automatically control the light coming in. Very high tech.
Okay.
But the people inside the building found the constant adjustments.
Hmm.
The whirring and shifting, even on slightly cloudy days, really distracting. Annoying, even.
Oh, right. Too much automation.
Kind of. It really highlights how crucial it is to think about the occupant's well-being. And, importantly, giving people the ability to override these automatic systems. Technology should help us enhance our experience, not just take over, right?
Absolutely. Finding that balance between smart automation and, well, human control. Okay, let's dive into some specific types now. These shape-changing materials sound fascinating. First up, expansion materials, or EMs. What's the basic idea?
Expansion materials, EMs, yeah, like the name suggests, these are materials that show a reversible change in their shape or their size directly because of temperature changes. They sort of expand when warm and contract when cool in a predictable way.
Okay, and where do we actually see these being used?
The source mentions N-alkanes. These are specific hydrocarbons, C10 to C18, basically colorless liquids at room temp. They work well at lower temperatures, so you find them in things like sprinkler systems for fire safety.
Ah, like the little glass bulbs?
Not quite the bulbs themselves, but components within valve systems. Also in thermostats for building heating, greenhouse ventilation, even in cars.
So it's a pretty established technology then. What are the pros and cons?
Well, the pros are pretty good for certain jobs.
Hmm.
They give you a continuous, fairly linear movement. They're compact.
Mm-hmm.
And a big one. They don't need electricity to work, so they can be inexpensive and reliable.
Okay, but the downside?
The main drawback is they tend to be a bit slow to react, not instantaneous. Sluggish, you might say.
Got it. The text gives a really interesting architectural example. The documentation center at the former concentration camp, Hinzert. What's happening there?
Yeah, this is quite a striking application. The foyer has this big, circular, frameless glass facade, but with a dynamic outer skin made of cladding panels.
Dynamic.
These panels are split diagonally and can pivot open to different angles, controlling the natural light inside. The clever bit is how they're controlled. They use EM working elements combined with thin film solar cells and special thermistors, PTC thermistors.
Okay, slow down. How do those work together?
Right. So the solar cells provide some power, and the thermistors are sensitive to temperature. Together, they allow the EM elements to adjust the panels based on the light levels inside. To make sure it's reacting mostly to light and not just the outside air temperature, the EM parts are housed in thermally insulated casings.
Wow, okay. So it's a light responsive system driven by temperature changes within the EM, triggered by the light hitting the solar cells and thermistors. That's clever.
It's a really integrated system, yeah. A material system reacting intelligently.
Okay, moving on to thermobimetals, or TBs. How are these different from EMs?
Thermobeam metals work on a completely different principle, based on how they're made. They're composite materials, basically, two or more layers of different metals bonded together. The key is that these metals have very different rates of thermal expansion.
Meaning they expand and contract differently when heated or cooled?
Exactly. One metal expands a lot, the other expands less.
So what happens when the temperature changes?
Because the layers expand or contract by different amounts, the whole strip or component is forced to bend or curve. The metal that expands less acts as sort of a passive anchor, while the one that expands more drives the bending motion.
Simple principle, but effective. Are there specific metal combinations that are particularly good for architecture?
Yes, the source points out one combination. A nickel-cobalt-iron alloy called super-invar, that's the passive low-expansion layer paired with the manganese-nickel-copper alloy as the active high-expansion layer.
And why that combo?
It's apparently very sensitive to temperature changes, which is good, and it resists corrosion well, which is obviously important for buildings. The downside is it tends to be more expensive than other options.
Makes sense. So what kind of architectural uses are we seeing for these?
A key area is creating kinetic building envelopes that respond to the weather. Axel Ritter's work in Germany is mentioned specifically. Imagine facades with vents or shading louvers that automatically open or close based on the outside temperature.
Self-adjusting buildings again. The text also mentions different forms of thermobimetals, strips, spirals, discs. How does the shape matter?
The shape determines the kind of movement you get. Simple strips can push or pull or act like temperature-sensitive springs. U-profile or reverse strips can give you longer straight movements. Spirals and helices can create rotation. Discs might be used for slower creep actions. Spring elements can compensate for thermal expansion elsewhere. Lots of options depending on the geometry.
Right, tailoring the form to the function. Axel Ritter's name comes up again with something called a polyreactive mechanomembrane. Sounds complex.
It does. His idea was inspired by biology specifically, trying to mimic the responsiveness of human skin in a building envelope.
Human skin? How so?
Well, skin can deform, change color slightly, regulate temperature. Ritter wanted to translate that multifunctional responsiveness into a technical membrane using various smart materials, including thermobimetals. The goal is a weather-driven system that reacts automatically.
That's quite an ambition. And there's another interesting example. These color indicator balls using both thermobimetals and hygrobiocomposites. What are they showing?
Okay, these are pretty neat. Imagine these modules with spheres that collect rainwater. Around them are these indicator balls. Some balls have thermobimetal springs and humidity-sensitive composite material. Others just have the thermobimetal springs.
They react differently.
Exactly. Because some react to both temperature and humidity, while others react only to temperature. The balls shift around, showing different colored surfaces. It becomes this kinetic, color-changing display that visually tells you about the temperature and humidity of the air around it, like a little weather station made of smart materials.
That's a really intuitive way to visualize environmental data. Okay, next up. Shape memory alloys, or SMAs. These always sound like magic. What's their secret?
Yeah, they do seem a bit magical. The key property of shape memory alloys is that they can remember a specific shape they were previously set to.
Remember. How?
Usually they're made of nickel titanium or maybe copper zinc aluminum alloys. If you deform them when they're relatively cool, bend them, twist them, they'll stay deformed. But then if you heat them above a specific transformation temperature, pop, they spring back to their original remembered shape.
So heat is the trigger to return to the original form. That's pretty amazing. What are people doing with this in architecture and design?
SMAs are finding more and more uses. As wires or rods, they can be actuators, things that create movement for positioning systems, making things move linearly or rotate. They can be woven into textiles.
Textiles. Like smart clothes.
Or smart curtains, yeah, creating fabrics that change shape with temperature. As thin sheets, they could potentially make self-healing or self-shaping surfaces, and we're even seeing them in things like variable connectors. The source mentions a hook and loop fastener, like Velcro, demonstrated by EADs.
SMA Velcro. How would that work?
Imagine the hook parts are made of SMA. You could potentially control the temperature to make them grip tighter or release more easily. A temperature-controlled fastener.
Clever. And the textiles. You mentioned curtains.
Right. Yvonne Chen-Villi did some really interesting work on shape memory interior textiles. She wove fine SMA wires alongside regular threads. When the temperature changes, the SMA wires contract, causing the whole fabric to change its structure, maybe bunch up, maybe flatten out.
So you could have curtains that automatically close when it gets too sunny and hot?
Exactly. Or privacy screens that adjust themselves. Or dynamic room dividers, wall coverings. It opens up possibilities for interiors that adapt on their own.
Very neat. The text also mentions SMAs in bridges. That sounds more heavy-duty.
Yes. Apparently in Italy, there's a bridge using passive struts made of SMA. These exhibit something called pseudoelasticity. Basically, they act like super springs that can absorb and dissipate energy, specifically from seismic forces, like built-in shock absorbers for earthquakes.
Wow, enhancing structural safety, that's a significant application. Okay, final category for shape-changing, electroactive polymers, EAPs. What makes these move?
Electroactive polymers, EAPs, change their shape when you apply an electrical stimulus. There are two main types. Electronic EAPs, where the movement comes from electrostatic forces like charges attracting or repelling, and ionic EAPs, where the shape change is caused by ions moving around inside the polymer.
So apply electricity and they bend or stretch. What kind of movement are we talking about?
It depends on the specific polymer and how it's set up. They can bend, expand, contract. You can layer them or coil them to make more complex actuators. Interestingly, the text notes, and this goes way back to Röntgen, the X-ray guy in 1880, he apparently saw an elastic band shorten when he zapped it with electricity.
No way! So this isn't entirely new then. What types of EAPs are relevant now for architecture?
Well, one example mentioned is acryl-based dielectric elastomers. These are electronic EAPs. They can apparently achieve pretty large shape changes, like stretching up to 380%. But the catch is they usually need quite high voltages to work, and they can be sensitive to moisture.
High voltage might be a hurdle. The book gives a really wild example of the Balnea NY swimming pool. What's that about?
Yeah, that's a really imaginative concept. Picture a swimming pool where the end walls are made of EAPs.
Okay.
Depending on what's happening in the pool area, these EAP walls can actually deform, creating little alcoves or niches that become individual sauna spaces.
The pool walls turn into saunas.
Exactly. They can even bulge outwards into the street, apparently, giving a visual link between inside and outside. It's a prime example of shape-shifting architecture responding to how the space is being used.
That's incredible. Talk about adaptable spaces.
Ah.
Okay, let's switch gears now to materials that change color or optical properties. First category, photochromic materials, PCs. What makes them change color?
Photochromic materials, PCs, change color reversibly when exposed to light, usually UV light, but sometimes visible or infrared. It happens because the material can exist in two different molecular forms, say form A and form B.
Huh.
Each form absorbs light differently. When the material absorbs the right wavelength of light, it switches from one form to the other, and that causes the color change. When the light source goes away, or maybe with heat or different light, it switches back.
Like those eyeglasses that darken in the sun.
Exactly like those. That's a classic example of photochromism.
Are there different kinds?
Yeah, the text mentions positive photochromism, going from light colorless to colored, which is most common, but also negative photochromism, going from colored to colorless when exposed to light. And the mechanism can involve one or two photons of light. They've developed more fatigue-resistant types over the years, like spiroxazines and even new photochromic glass types.
So beyond sunglasses, what are the potential uses in buildings or design?
Well, you could have UV-sensitive wallpapers or textiles, maybe clothing that changes color. But beyond just aesthetics, they could be used as indicators showing, say, the energy state of something or how much time has passed, or even mapping surface temperature changes visually.
The text mentions the appearing pattern wallpaper project. Tell me about that.
Right, that was developed in Sweden. It's a wallpaper printed with UV-sensitive inks. Under normal indoor light, it looks plain, monochrome, but shine UV light on it, and a red pattern appears.
Why would you want that?
The idea was partly to make us more aware of invisible energy, like UV radiation, in our environment, a visual cue for something unseen.
Interesting. Okay, next. Thermochromic and thermotropic materials. TCs and TTs. How are they different and what do they do?
Both react to temperature. Thermochromic materials, TCs, change color reversibly with heat or cold. Thermotropic materials, TTs, change their optical characteristics, like how transparent or translucent they are with temperature changes.
Got it. Color versus transparency. What are some examples?
For thermochromic, you've got things like cholesteric liquid crystals used in mood rings, like you mentioned,
Right.
and leucodyes. Also some inorganic compounds. For thermotropic, you might have polymer blends, other liquid crystals, some resins, and also phase change materials, PCMs, which we'll get back to later under energy storage. A key development is switching hydrogels for solar protection that go from clear to cloudy based on temperature.
So beyond mood rings, are there serious architectural uses for thermochromics?
Oh, absolutely. Thermochromic paints are being used in art and design to visually show temperature differences on surfaces. Sigmar Polk did a wall installation. J. Mayer H. did room installations using this effect. People are researching putting thermochromic pigments in concrete for displays on facades.
Concrete displays.
Yeah, imagine the building surface changing color to show temperature patterns. And thermotropic layers in glass are really promising for automatically controlling light and heat entering buildings, potentially reducing heating and cooling needs.
Tell me more about those art installations, Pulp's Thermowand and J. Mayer H's In Heat.
Okay, Polk's Thermowand Thermowall used a large curved wall coated with thermochromic paint. The idea was that as sunlight hit different parts of the curve with varying intensity, the temperature differences would create shifting shadow drawings in color on the wall itself.
Wow, dynamic art driven by the sun.
Exactly. And J. Mayer H's In Heat installations used thermochromic paints sensitive to human body heat. So when visitors touched the walls, they'd leave temporary handprints or outlines in a different color. It really blurred the lines between the building, the art, and the person interacting with it.
That's really interactive. Okay, next we have electrochromic and electro-optic materials, ECs and EOs. These react to electricity, right?
Correct. Both change their color or optical properties when you apply an electric field. Electrochromic materials, ECs, merely change color and opacity. Electric-optic materials, EOs, usually change transparency or how they bend light, their refractive index.
What have been the big steps forward here?
Well, the basic ideas go back a bit. Krauss worked on tungsten trioxide in the mid-20th century. The 70s saw key principles established, even the first e-pater concepts. For electro-optics, things like PDLCs, polymer-dispersed liquid crystals, used in privacy glass like Privalite came along in the early 90s.
Privacy glass, the stuff that goes from clear to frosted.
That's the one. Switchable transparency. A big recent step for electrochromics has been developing green electrochromic polymers. That's important because having good red, blue, and green means you can potentially create a full spectrum of colors.
So we're talking smart windows that tint on demand or go opaque, maybe even automatically?
Precisely. Electrochromic glass like PDLC can switch very quickly between clear and translucent, great for privacy, or even as projection surfaces. Electrochromic glazing is also being used more, even retrofitted into older buildings, to actively control sunlight and heat gain. The text even mentions a big electrochromical facade in Tokyo.
The source mentions specific polymers like polyaniline and polythiophene. What do they do?
Right, those are examples of conductive polymers used in the active layers. Polyaniline, for instance, can change from transparent to green to violet depending on the voltage. Polythiophene can shift between red and blue hues. These organic materials offer potential for more colors, though maybe sometimes face challenges with long-term stability compared to the inorganic metal oxides.
It definitely feels like smart glass is becoming a real practical option for buildings. Something different. Adhesion-changing smart materials. How do these work?
These are interesting. They can change the forces of attraction adhesion between their surface and other stuff.
Hmm.
This change is triggered by a stimulus, like light, temperature, or an electric field.
Okay, and the text focuses on photoadhesive ones, specifically titanium dioxide, TiO2. What's special about TiO2?
Titanium dioxide, especially in a form called anatase, has this really useful property. When UV light hits it, it acts as a photocatalyst. It helps chemical reactions happen, can break down organic pollutants, dirt, grime on its surface. And at the same time, the UV light makes the surface hydrophilic.
Hydrophilic, water-loving.
Exactly. Water attracting.
So how does that affect adhesion?
Because the surface becomes hydrophilic, water doesn't beat up on it. It spreads out into a thin film. This film of water can then easily wash away the dirt and pollutants that the photocatalysis has already started breaking down.
So it's the basis for self-cleaning surfaces.
Precisely. You see TiO2 coatings used on self-cleaning paper, ceramic tiles for building facades, even construction membranes. The Obayashi Corporation chapel is mentioned as having a self-cleaning membrane skin.
That's pretty useful.
And there's a bonus. The photocatalysis also helps clean the air around the building by breaking down airborne pollutants, like nitrogen oxides. The source mentions a study suggesting 1,000 square meters of TiO2 surface could have the air cleaning effect of about 70 trees.
Wow, self-cleaning and air purifying. That's a double win. Okay, let's move to materials that actually emit light. First, photoluminescent smart materials. What's the difference between fluorescence and phosphorescence?
Right. Both involve emitting light after being energized, usually by UV light. Fluorescence is immediate, absorbs energy, emits light almost instantly, stops when the energy source stops. Phosphorescence has a delay. It keeps glowing for a while, minutes or even hours, after the excitation stops. It stores the energy briefly.
Okay, immediate versus delayed glow. Where are fluorescent materials used in design?
Well, the text mentions UV reactive liquids for textiles, creating effects under blacklight. Artist Christina Kubish used them in light installations. They can be visually striking, but maybe can degrade over time with UV exposure.
And phosphorescence. We know glow-in-the-dark stuff. Any more advanced uses?
Sure. Phosphorescent paints are crucial for safety marking escape routes, for example. They use pigments mixed into binders like acrylate or even sugar solutions. But artists are using them too, with Hanshin's light installations. Julia Quintero's luminous wallpaper using that sugar solution method. Annalisa Hailati even wove phosphorescent threads into fabric.
So crossing from safety to art. Interesting. Now, electroluminescent smart materials. How did these make light?
Electroluminescence is light emission caused by an electric current passing through a material. There are different types based on how it works. Injection EL like LEDs, powder EL, thin film, thick film EL, and polymer small molecule EL like OLEDs. We'll focus on LEDs, thick film EL, and OLEDs as they're most relevant for architecture right now.
Okay, LEDs. We know those well. How are they being used innovatively in buildings?
LEDs, light-emitting diodes, are everywhere now, right? Especially since the development of blue LEDs made efficient white light possible. We're seeing ultra-flat LEDs integrated right into glass panels, making illuminated railings or room dividers. The Cloud9 facade in Barcelona is a wild example. Thousands of LEDs with tiny solar cells powering RGB LEDs create this huge dynamic color display on the building.
That sounds incredible. What about thick film electroluminescence, EL? How's that different?
Thick film EL works by putting an electric field across a layer of luminous pigment, like a phosphor, mixed in a binder. It excites the phosphor, making it glow a cool, flat, diffused light. Think EL films, strips, even cables.
So not a point source like an LED.
Exactly. It's an area light source. And it can be flexible, put on curved surfaces. That's why it's used for backlighting LCD screens and in flexible signs. Loop.ph Ltd used EL printing for light kinetic room dividers and installations, showing off that flexibility.
Flexible light sounds useful. And finally, OLEDs, polymer small molecule electroluminescence. We see them in screens, but what about buildings?
OLEDs, organic light-emitting diodes, use thin layers of organic materials that light up when electricity passes through. Key advantages.
Yeah.
They emit diffuse area light, don't need a separate backlight like LCDs, and can potentially be made flexible, even transparent.
Transparent light sources.
Yeah. Still emerging for architecture, but the potential is huge. Think flexible displays on walls, transparent OLED windows that are screens by day and lights by night, maybe emergency lighting. The smart wrap concept imagined a building skin integrating OLEDs and other functions, a real glimpse of the future.
Definitely sounds like OLEDs could be transformative. Okay, shifting again. Materials that generate electricity. First, photovoltaic smart materials, specifically dye solar cells, DSCs. How do they work?
Dye solar cells, DSCs, kind of mimic photosynthesis. You have a transparent conductive layer coated with nanocrystalline titanium dioxide, that TiO2 again, which is a semiconductor. Then you add a light-absorbing dye. There's an electrolyte and a counter-electrode too.
And the sunlight.
Sunlight hits the dye, excites electrons in the dye molecules. These electrons jump into the TiO2 layer, and that starts the electric current flowing.
What's the advantage over standard silicon solar panels?
Well, DSCs can work reasonably well even in lower light or diffuse light conditions. They don't need blazing direct sun as much. Plus, and this is big for designers, they can be made colored, even semi-transparent. So you could integrate solar generation into facades or roofs much more aesthetically. Diesel's a company pushing this technology.
Colored, transparent solar panels. That would change the look of solar tech completely. Next, thermoelectric smart materials, TEGs. How do they get electricity from heat?
Thermoelectric generators, TEGs, use the Seebeck effect. Basically, if you have a temperature difference across a junction of two different semiconductor materials, N-type and P-type, it generates a voltage. TEGs usually string lots of these junctions, thermocouples together, hot on one side, cold on the other, and you get electricity. There are also element-based ones that work a bit more like solar cells with heat.
Where might these actually be used? Are they efficient?
Efficiency is still generally lower than other methods, but they're useful in niche areas, anywhere you have waste heat, basically, or maybe concentrating solar heat onto them. Micropelt is making tiny TEGs to power sensors. And there's research into putting flexible TEGs into building membranes to generate power from the natural temperature difference between inside and outside.
Harvesting waste heat or small temperature differences. Clever. Finally, for electricity generation. Piezoelectric smart materials. PESPEPs. What's their trick?
Piezoelectric materials generate an electrical charge when you mechanically stress them, squeeze them, bend them, stretch them. It's a direct conversion of mechanical force to electricity.
And they work the other way too.
Yes, that's the inverse effect. Apply electricity and they deform. You have piezoelectric ceramics, PECs like PZT, and polymers, PEPs like PVDF.
What are the architectural applications?
Mostly sensors detecting pressure, vibration, strain. And actuators using the inverse effect for small, precise movements, multi-layer benders, things like that. MFIT technology uses electric polymer films for pressure sensors. Axel Ritter used PEC elements in a sound installation controlled by light. The text also mentions a weight-controlled pavilion concept using related mechanical principles.
Force into electricity, electricity into force. Very direct. Okay, nearing the end, energy exchanging smart materials. These store energy.
Yes, they can store energy light, heat, electricity, even hydrogen, and release it later, reversibly. We'll focus on the heat-storing ones. Phase change materials, PCMs.
We mentioned PCMs briefly before under thermotropics. Remind me how they store heat.
Right. PCMs store and release heat when they change phase, usually melting from solid to liquid or freezing back from liquid to solid. They absorb a lot of heat while melting at a constant temperature and release that heat while freezing, again at a constant temperature. This is called latent heat storage.
So they act like thermal batteries, absorbing heat when it's hot and releasing it when it's cool.
Exactly. Great for temperature regulation. NASA used them way back in the 60s for spacecraft. Now we have lots of types: paraffins, salt hydrates, fatty acids, even waterous. A key development is microencapsulated PCMs, like micronal tiny capsules of PCM you can mix into plasterboard, concrete, etc. You also see PCM in foil bags or integrated into special insulation glazing like Glass X.
So you could have walls or windows that actively soak up heat during the day and release it at night.
Precisely. PCM plasterboard is used in low-energy buildings to smooth out